In the last section, we discussed atoms, and in those atoms we said, they're made of protons, neutrons, and electrons, and that the number of protons in each atom determines what element that substance is. And there are various substances that we have around, things like iron, gold, oxygen, that are made up of only one type of atom or one type of element. But most of the other substances that we have here on Earth that are pure substances, ones that are made of only certain ratios of atoms, are called compounds. And so a compound is basically a case where you have a certain number of atoms of certain elements that bond together and they form these pure compounds. And so some examples of these would be water. There's no water on the periodic table as an element. It's instead H2O, hydrogen and oxygen atoms, 2 hydrogen, 1 oxygen. Table salt, NaCl, sodium chloride, or even ammonia, NH3. These are all substances that are compounds because they're formed of multiple atoms that are in a constant ratio. So these bonding in these types of compounds is due to one of two types of things. One possibility is that the atoms either lose or gain electrons to form oppositely charged ions, which then attract to one another. And so when that happens, that's called ionic bonding. The other possibility is that the two atoms might share electrons, and when they share electrons, it's called covalent bonding. And so if the two atoms or the multiple atoms in the compound form ions, they completely lose electrons or completely gain electrons, then they ionically bond and form an ionic compound. If they, on the other hand, do not completely lose or gain electrons, instead they just share them, then we'd say it's a covalent compound. The reason why this happens, why that atoms tend to gain or lose electrons, is because that they want to lower the total potential energy of the electrons that they have. And oftentimes you can end up, when a compound, with a total potential energy ending up being lower in the compound than it would be if the electrons were just in the lone atoms by themselves. And so that's why they form these. So first one we'll look at is ionic compounds. So atoms which hold on to their electrons more loosely are called metals. And so if you look at your periodic table right here, this group right here, and let's see, sometimes you'll count these in here as well, but that group all the way over on this side, all of those atoms are generally metals. And of course these are sort of these reddish ones that sort of work in here are sometimes called semi-metals or metalloids. They have some characteristics like metals, some like non-metals. But the ones that are sort of in that bluish gray are metals. They are more likely to lose their electrons because they hold on to them more loosely. And we'll go into a lot of detail on that later on. The atoms that are on the other side over here, the ones that sort of fit into this section, those elements right in there. And once again, also potentially including these, which sort of are on they're the semi-metals, the ones that have characteristics of both metals and non-metals. But this section primarily right over here, those are your non-metals. They tend to hold on to their electrons tightly, and they tend to attract electrons, outside electrons, more strongly. They're non-metals. So your metals are more likely to lose some of their electrons, and so if they lose their electrons, as we sort of talked about previously, they're going to become a positive ion. Those are called cations. If they are a non-metal over here, then they pull in outside electrons and we're likely to gain electrons from other atoms. They'll become negative ions that are then anions. Okay? So what will happen is that we'll end up with this cation, which has a positive charge, and we end up with this anion, which has a negative charge, and positives and negatives charges tend to attract towards one another, and so it pulls these two together and they stick together, and that's basically what an ionic bond is. Now, it doesn't tend to happen, they're just pairs like this. They actually tend to form large groupings, and so that's this image that you can sort of see over here on the right is an example of sodium chloride. NaCl, in this case, the little bluish, purplish ones are the chlorines. They tend to end up being an anion. They're going to have a negative charge right there. The sodiums are the green ones right here. They'll have a positive charge. And so you can see that each of the positive sodiums, the green ones, are surrounded by negative chlorines because since the sodium ions are positive, they attract in the negatives and they form these large masses. like this. And so, as it says down here, each cation is surrounded by many anions, and then similarly, each anion is surrounded by many cations. You can see that, like say that this particular green one is surrounded by the purplish chlorines, but in the same way, each purplish chlorine is surrounded by the positive sodium ions like that. But the ratio, in this case, is a 1-to-1 ratio. For every single one chlorine, there is one sodium, like that. And so the ratio of cations to anions in this network of ions here determines what the chemical formula of the substance is. And so that would be like we'd say NaCl right here. This smallest ratio in an ionic substance is called a formula unit. Okay? Formula unit is always used for all types of compounds, though it's the only thing we can use for ionic compounds. We'll find out in just a second that for covalently bonded compounds, we will usually use another term, even though formula unit is completely appropriate for all types here. So that's what happens in an ionic compound. Now, covalent compounds, on the other hand, are cases where the atoms don't completely lose their electrons, instead they share them. And so the picture that we have over here on the right shows oxygen, and so they're just for purposes of illustration in this model, showing oxygen as the red, and the red dots indicating the electrons for oxygen. You can see that there's one electron for oxygen that's being shared in between this hydrogen and the oxygen, and there's one down here for the oxygen that's being shared with the hydrogen, and likewise the hydrogens, which are white, are sharing electrons here and here with the oxygen. And so that act of sharing holds these atoms together. So they don't form ions. Instead, the atoms simply share their electrons. And so when that happens, what you've got is a covalent compound. Okay? Covalent compounds don't form the large networks. They are not the large networks like you see with ionic compounds, like we saw previously, where you can see all of the different ones all joined together like that, where they're surrounded by multiple ones. Instead, is in covalent compounds, they form individual groups of bonded atoms, which are called molecules. Okay? And so here we have one water molecule, two hydrogens, and one oxygen, H2O. Okay? And so we wouldn't use the term molecule with an ionic compound. We use the term formula unit with that because the ionic compound forms the large networks. But with covalent compounds, we will use the term molecules, though formula unit is okay to use. Okay? So as we said, a molecule, smallest unit of a covalent compound. The number of each atom in the molecule is the compound's chemical formula. So H2O, because it has two hydrogens and one oxygen in that molecule. So one other thing we need to look at, there are some compounds that have both ionic and covalent bonding in them. So what will end up happening here is you'll end up with a group of atoms which are covalently bonded to one another. Okay? And so, but what happens is, unlike a molecule, in a molecule when they bond together, the total number of electrons shared ends up meaning that the molecule is electrically neutral. There are in the whole molecule the same number of protons as there are electrons. And so it sits by itself, it's neutral, so because it's neutral, it's not going to attract anything else and to form a larger compound. But for this particular group, sometimes these covalently bonded atoms will have an overall ionic charge. And if that happens, the term that's used for them is they're called polyatomic ions. You know, that root poly means many, atomic atom. So this means a many atom ion. And so an example of this might be NH4, like this. Looks like this might be a molecule, but it turns out whenever you actually look at this in detail, you'll find out that there is a missing electron. Is that for this particular thing, is that I believe that there are, let's see, what would it be? A total of 11 protons and only 10 electrons. And so as a result, there's an overall positive charge that's on this. And so that NH4 is not a molecule because it has that positive charge up there. And so if you ever see an ionic charge on something that looks like it's a molecule, it's not a molecule. It's instead one of these polyatomic ions. Now these polyatomic ions, they can either be cations, so that's that NH4 we just talked about, because it has the positive charge up here. They could also be anions, like for example, this is phosphate right here, PO3, 3-, and that 3- tells you the charge of the whole polyatomic ion, the whole PO3. And so what will happen is while the polyatomic ions are covalently bonded to each other, so the P is covalently bonded to these 3 O's right over here, is that since they're ions, they can form ionic bonds with oppositely charged ions. And so for this one right here, if someone were to go and bring in, say, a chlorine ion, like this, is that the positive right here would attract with the negative right there, and so as a result that these two would bond together and form an ionic bond, and you'd end up with a compound that would, in this case, be NH4, that's a 4, Cl. So you have a polyatomic ion right here, ionic compound, so that's our positive one. The chlorine is the negative one. We have this, so this would be the formula unit of this particular ionic compound, even though there is covalent bonding within that polyatomic ion right there. So let's look at molecular formula. Figure out how do we know how many type of atom is in a formula unit or in a molecule. So the chemical formula is also, this is also called the molecular formula, even though technically molecular formula would only mean for covalent compounds. We'll use the term molecular formula in this class to refer to both covalent and ionic substances. So just know if we say what's the molecular formula of an ionic substance, what we're really meaning is what is the formula for the formula unit for that. It's just a little more easy to say molecular formula than chemical formula unit. So the chemical formula or molecular formula for any compound is the smallest unit for that compound. And so the molecular formula tells how many of each atom are in the formula unit or molecule. So let's take, say, H2O down here. And so H2O is a molecule because these are covalently bonded. And no way that we know of just yet to tell whether it's covalent or ionic, but we treat them the same way as far as figuring out how many atoms are in each one. So the way this works, and this is something that you see in other classes, is that the 2 that's right down here is a subscript, tells how many of the previous element there are here. And so that 2 tells you that there must be here 2 hydrogens in this particular molecule. The oxygen, our next one right here, there is no subscript down there. When you see no subscript, that's an implied 1. So this would mean there are 2 hydrogens and 1 oxygen in this molecule of water. Okay? Now if there's a polyatomic ion, as we're going to see in the next one here, this Ba, open parentheses, OH, close parentheses 2, one way we can indicate it is by putting the polyatomic ion in parentheses. That's only necessary if there's more than one of them. But let's go through and figure out how to determine how many different atoms are in this molecule here, in this compound. So this formula unit. So we have Ba, barium, we have oxygen, and we have hydrogen. So let's see if we can figure out how many in each one. So first thing is barium. So for the barium, you'll notice there is no number after the barium right here, which implies it's a 1. It's like in algebra, if you just see X, that means there's only one X. Oxygen's our next one. So for the oxygen, there's no number after the oxygen, which would mean that's implied a 1 right here. But because of the fact that it's in parentheses, we have to look at the number on the outside of the parentheses. And so this number is a 2. So that 2 distributes into each of the things that are inside of that parenthesis, inside those parentheses. So there's 1 oxygen inside the parentheses, but there's a 2 on the outside of the parentheses, which means there are 2 OHs. So a total number of oxygens of 2. Hydrogen, there's also no number down there, which implies a 1. So there's 1 hydrogen in OH, but there are 2 OHs, so a total of 2 hydrogens. If, for some reason, this had been something that was in parentheses that was not just one of each one, so one like this, Ba, open parentheses, NO3, and then a 2 on the outside, that there would be 2 nitrogens because there's an implied 1 right there times the 2 that distributes gives you 2 nitrogens, and there would be 6 oxygens because there are 3 oxygens that are right here, then inside in an NO3, and there are 2 NO3s, so the total would be 6 right there. Now, another thing that you'll run into is a coefficient that's in front of the formula. So the way the coefficient works is it's not part of the molecule, it just tells you how many molecules or how many formula units you have. So in this case is that we have 3 FeCl3 units. And so if we just said how many Fe's, how many irons are in this right in an FeCl3 molecule or formula unit, then we would just say 1. But if we said how many Fe's are in this whole thing, we'd have to say 3. because there's an implied 1 right there. There's no parentheses, so we don't have to worry about that. And so there's 1 Fe in FeCl3, but since we have 3 total FeCl3s, that means we have 3 iron atoms. For chlorine, there are 3 chlorines right here, and in 1 FeCl3, and then since we have 3 FeCl3s, that means a total of 9 chlorines, 3 3s right in there. And so that's how you'd work out the number in a molecular formula.
So this one asks how many atoms of oxygen are in each of the following. So for our first one right here, we say, all right, let's take a look. Is there a subscript directly after the O? The answer is yes, it's right there, that 2. And so in this case, there is no number out front, so that means it's a 1. We don't have to worry about that. There's no parentheses here, so that means there are just 2 oxygens in that one. This one right here, there is no subscript after the O. There's no parentheses in here, so there's just 1 oxygen in NaOH, but there are 3 NaOHs, so 3 times 1 gives me 3. 3 oxygens in number 2. All right, our next one, Al2SO43. So in this one, there is a 4 after the oxygen, so we have at least 4 of those, but the 3 distributes that. So that means that there are 3 4s, or 12 oxygens right here. No number out front, so we don't have to multiply it by anything. For this next one, we have 3 oxygens in that little piece right there, but the 2 distributes, so that means we have 3 times 2. We have 6 oxygens in this guy right here, but then we have another 6 out here, so we have 6 6s for a total of 36 oxygens in number 4. And that's how you'd work that out. For molecular mass. First thing, before you talk about molecular mass, you have to talk a little bit about atomic mass. And we discussed that a little bit earlier, but the atomic masses that you want to use for finding molecular mass are the ones that are on the periodic table. The only ones you won't use, the ones in the periodic table, are looking for neutrons, because those have to be whole numbers. The atomic masses that are given on the periodic table are basically averages of all the different isotopes at the levels that you'd find them on Earth. After the ding, we'll continue here. So for a molecular mass, what you have to do is the first step is to figure out how many of each atom are in your particular molecule. And so in this case right here, we have 2 elements. We have silicon and we have fluorine for this example. The next thing to figure out is the number, as we said. So we have how many silicons here? We have 1. How many fluorines? We have 4. All right. The next thing to figure out is going to be the atomic mass, like that. So we look at it for silicon. So silicon has, look up silicon here, has an atomic mass of 28.09. And we do want to always round these to the hundredths place. Fluorine, looking that up, fluorine has a mass of 18.998, which rounds up to 19.00. All right. So once we've got these 2, the next step is basically what we can do is you multiply the number of each one times the mass of each one, and that's going to give you a total mass of each one. And so 1 times 28.09 just gives us 28.09. 4 times 19 is one that I should be able to do in my head, but I'm going to do it in the calculator just to make sure I don't make a mistake. So we said 4 times 19 is 76. And so we get 76.00 is the total amount of fluorine. And now at this point, to find the rest of this, we can just go ahead and add those 2 guys up. And so we would say 76 plus 28.09. So plus 28.09, and so we get a total of 104.09. And the unit is going to be AMU. For right now, we'll find there actually is another unit you can use, but this is the one that we will have for right now. So 104.09 AMU would be what we have for the molecular mass of SiF4, silicon fluoride. So on our next one, we're going to set this up the same way. This one, though, has 3 elements in it. So we have barium, we have carbon, and we have oxygen. So let's first look at our number of each one. Looking at this, we have 2 bariums. Carbons, we have 1 that's inside here, but the 3 distributes, so that means we have 3 carbons total. Oxygens, we have 3 inside the parentheses, but the 3 distributes, gives us 9 oxygens. So for the atomic mass that we'll have here is the first one is barium. Looking at barium, it's sort of towards the bottom left, 137.33. Our next one is carbon. Looking that up, we have 12.01. And oxygen is our last mass here, 15.999, which rounds to 16.00 to the nearest hundredth. Once again, is that all we have to do is multiply the number of each atom times the atomic mass, and that'll give us the total mass of each one. And so, once again, it's calculator time. So we take our barium, so we have 2 times the mass of barium, 137.33. And for that we get 274.66. For carbon, 3 times 12.01. We multiply that together, we get 36.03. If you do the math on that. And then our last one, 9 times 16, which gives you 144.00. That's 0.00. And now at this point, as we did before, all we have to do is just add up those 3, and that will tell us the molecular mass of this compound. So we'd say the 274.66 plus 36.03 plus 144, and doing so gives us 454.69. So 454.69 AMU, or atomic mass units. And so that right there is going to be our final answer here on how to find molecular mass.